Imagine you need to run to the grocery store to grab, I don't know, a carton of milk. It's a 10-minute round trip.
Right, super quick.
Yeah, exactly. You walk out to your driveway, but instead of just pulling out your car keys,
Yeah.
unlocking the door, and starting the ignition, you realize you have to build your car's engine from scratch.
Oh, man, just to get some milk.
Right. You have to smelt the iron, cast the engine block, machine the pistons, assemble the whole thing right there on your driveway. And only then can you actually drive to the store.
Which is obviously insane. I mean, you would never do that in the physical world. You just buy an assembled car and use it.
Exactly. But in the world of software engineering, and specifically C++ development, this is literally what developers have been doing for years.
Yeah, it's a massive pain point.
We're talking about compiling these huge, heavy dependencies from scratch over and over again, every single time they set up a fresh workspace. So today, we are taking a deep dive into a masterclass in eliminating that exact friction.
It's a really elegant solution, too.
It is. We are pulling from a 2026 presentation by a developer who goes by Luck036. It's titled CMake CPM Optimization. Stop recompiling everything. And it details how a shockingly simple code tweak managed to slash software build times from 15 minutes down to 30 seconds.
That kind of speed up is it's game-changing for a development team.
Totally. So whether you're a seasoned C++ engineer or just someone fascinated by massive efficiency gains, this deep dive will show you how working smarter yields incredible results. Okay, let's unpack this.
Yeah, so to really understand the brilliance of this optimization, we first have to look at the agonizing bottleneck these developers were actually facing during a clean build.
Right, the whole smelting the iron on the driveway thing.
Exactly. When you wipe the slate clean, to ensure your code is compiling correctly from the ground up, you rely on a tool to fetch your external libraries. And the primary villain in this scenario is the standard workflow of a dependency manager called CPM.cmake.
Which stands for CMake Package Manager, right?
Yeah, exactly. And its default behavior is just stubbornly inefficient. Every time a developer ran a clean build, CPM would download the raw source code for these dependencies and recompile them totally from scratch.
Which just sounds completely wild when you look at the sheer scale of modern C++
Yeah.
libraries. The presentation highlights this foundational dependency called absil CCP.
Oh yeah, Absil's huge. It's used everywhere.
It is, and it has over 400 .cc source files. So compiling absil CP on a first build takes anywhere from 5 to 15 minutes. You are literally just staring at a loading screen before you can even test, like a tiny one-line change you made to your own code.
Yeah, it completely kills your momentum. And the C++ compilation model is notoriously slow by design anyway.
Because of the headers and stuff.
Right. Unlike modern languages where a compiler can just read a precompiled module, a C++ compiler often has to parse massive header files and instantiate these really complex templates for every single translation unit.
So it's doing the exact same math over and over.
Exactly. When you force your local machine to do that heavy lifting for a massive library like Absil, you are burning CPU cycles for absolutely no reason. And even smaller libraries like FMT and Speedlog.
Right, the source mentioned those. They only have maybe 15 to 20 files each.
Yeah, but they still take 30 to 60 seconds a piece to compile. It adds up fast.
Well, wait, I was reading the source notes, and I immediately thought, don't we have caching for this? The presentation specifically mentions a flag, CPM and source cache. So if the files are cached, why are we still compiling?
Well, the source code itself might be cached, meaning you don't have to re-download all the text files from GitHub.
Okay.
But when you have a clean build directory, CPM still has to process the entire CMake configuration. It has to generate the build system, reconfigure everything, and reconfirm all the compiler targets.
Ah, I see.
Yeah, it creates what the presentation calls the works on my machine trap. A developer with a warm cache and an existing build tree on their primary workstation thinks everything is lightning fast.
Because they've already paid the price of that initial build.
Exactly. But the moment they need to clone the project fresh on a laptop or, a new developer joins the team, their workflow just grinds to a halt. They are stuck smelting the iron.
I had to push back here, though, because as I was digging into CPM's documentation in the source material, there is a built-in toggle designed specifically for this issue, isn't there?
You're talking about the local packages flag.
Yeah. It's a flag called CPM UC local packages equals true. If you just set that, shouldn't CPM just look for the pre-built package on the local machine and use that automatically?
You would think so. The logic totally makes sense. But Lux 036 details a fatal flaw in relying on that automatic toggle. And it all comes down to the chaotic nature of naming conventions in the C++ ecosystem.
Naming conventions, of course.
Mhm.
It's always naming conventions.
Always. Let's stick with Absale CPP as the example. Say you install Absale using your Ubuntu operating system's package manager,
It's
right?
like using apt-get.
Exactly. It pulls down a package that's often called libabsaledev and installs it on your system under the umbrella of Absale CPP.
Okay, makes sense.
But inside your actual project's CMake configuration, the internal target name it expects to find is just Absal.
Oh, wow. So they're speaking two completely different languages.
Exactly. CMake asks the system, hey, do you have a package called Absal? The system looks at its inventory, sees Absal CPP, and says, nope.
So CMake just shrugs, goes right back to downloading the source code, and compiles all 400 files from scratch.
Yep. System package managers like Linux's apt and build systems like CMake, they were built by completely different communities, often years apart. They just have differing philosophies on how things should be named.
So the automatic bridge between them fails because it basically requires a perfect one-to-one string match.
Exactly. If the automated system is just going to blindly look for the wrong name and fail, you have to take the steering wheel back. You need to manually tell CMake exactly where to look and, what alias it might be hiding under.
Which brings us to the actual fix. This is where we get the two-step fallback pattern that Lux 036 implemented.
Right. Instead of just giving CPM a single command to add the package and hoping for the best, you break it down. You give it 2 explicit manual instructions.
So step 1 utilizes a standard CMake command called find package.
Oh, right.
But the presentation notes the crucial detail here is appending a quiet flag to that command. Because if I remember my CMake correctly, find package is usually pretty aggressive.
Oh, very. By default, if it can't find the library you're asking for, it throws a fatal error and just crashes the entire build process.
Which is terrifying if you're trying to make a smooth developer experience.
Exactly. But adding that quiet flag changes the entire nature of the command. You are essentially telling the build system, hey, take a look around the local operating system for this specific package.
Okay.
If you find it, fantastic, link it up. But if you don't find it, don't panic. Don't throw an error, just stay quiet and let's move on to the next step.
It's defensive programming. I love that. So step 1 is quietly looking for the pre-built system package using its known system name. And if it finds it, boom, you are done in milliseconds.
Exactly.
But if it fails, step 2 kicks in, which is the CPM fallback. You basically tell CPM, okay, we didn't have it locally. Go ahead and download the source and build it the old-fashioned way.
And the real beauty of this 2-step process is how aggressively cross-platform it is.
Because modern development teams are so fragmented now.
Oh, totally. You have developers on Linux, Mac OS. Some are even experimenting with mobile terminal emulators. And every major operating system already maintains repositories of these common libraries.
So you're tapping into work that's already been done.
Exactly. The maintainers of those operating systems have already spent their CPU cycles compiling ABC into a neat, ready-to-use binary. Why should you do it again?
The source actually outlines exactly how this maps out in practice, which I found fascinating. On Ubuntu, the find package command seamlessly hooks into the system paths where apt installs things, finding libabsale.
Right.
And then on Mac OS, it checks the paths used by Homebrew. So it pulls whatever you got when you ran brew install absale.
It's so seamless.
It even works on Termux, which is a terminal emulator for Android. It checks for the binaries installed via PKG, installed absale TPP.
You are leveraging the incredible kind of invisible labor of thousands of open source maintainers who already built the engine for you.
And what I really want to point out to you listening right now is why this specific approach is the holy grail of system optimization. It is entirely zero risk.
Yeah, that's the best part.
Think about it. Let's say a developer hasn't run their Homebrew updates in a year. Or maybe they're on a totally fresh bare metal machine with literally no system packages installed at all.
The build doesn't break.
Exactly, the build doesn't break. The find package command stays quiet, the process gracefully degrades, and it just defaults back to the old CPM behavior. It takes 15 minutes, exactly like it used to.
At worst, your build is just as slow as it was yesterday. At best, it's lightning fast. It is a strictly dominant strategy.
But as with any architectural shift, the moment you try to scale this elegantly simple idea, you hit a wall.
And in software development, that wall is almost always Windows.
Here's where it gets really interesting. The transition from Unix-based systems to the notoriously tricky Windows environment. The source presentation details a massive complication they discovered during testing.
Right, when this cross-platform solution collided with Windows using a package manager called Conda.
Conda is the package manager that's super popular in like scientific computing and Python ecosystems, right?
Yeah, exactly. But it also handles C++ binaries really well. So on Windows with Conda, the two-step fallback initially looked like a huge success.
Okay.
The find package command ran, and it successfully located a pre-built system version of the FMT library. Specifically, it found a compiled file called fmt.dll.
Which is exactly what we designed it to do. It found the system package. Success.
Success, right. Except the project had another dependency, a very popular logging library called speedlog.
Uh-oh. I see where this is going.
Yeah. Now, speedlog wasn't found on the Conda system, so the script correctly fell back to step 2. It told CPM, hey, download the source for speedlog and build it.
Which it did.
Right. But here is the hidden trap. speedlog, by default, decides to bundle its own internal copy of the FMT library.
Oh, man. Because library maintainers are terrified of version mismatches.
Exactly. If the team behind speedlog knows their logging tool relies heavily on FMT, they want to absolutely guarantee you have the exact version of FMT they tested against.
They don't trust whatever random version you might have floating around your hard drive.
Nope. So they just shove a copy of it directly inside their own library source code.
Which creates a catastrophic collision.
Yeah.
Because the wider project is now trying to link against the pre-built system fmt.dl that it proudly found via Conda, and is trying to link against the newly compiled internal FMT this speedlog just built.
Yeah, it's a classic linker conflict.
For anyone who hasn't fought a C++ linker before, it's not like having two different instruction manuals for IKEA furniture. It is like having two people in your phone's contact.
Both named John Smith.
Yes, both named John Smith. When your code yells, call John Smith, the linker, which is the part of compiler responsible for connecting all the pieces together, just panics.
It sees two identical definitions for the exact same function, has absolutely no idea which John Smith you mean, and completely crashes the build.
So how did they fix it?
To solve this, Lux036 had to really dive into the specific configuration options of the dependencies themselves. They found a specific flag spdlog fmtexternal yes, and added it to the speedlog CPM fallback configuration.
Ah, so you are explicitly telling speedlog, hey, I know you brought your own John Smith, but do not use him. Use the external one we were providing from the system.
Exactly. You force speedlog to rely on whatever FMT library the wider project has already resolved. And the presentation notes, they actually found this specific flag missing in 3 different repositories during their rollout.
Wow, they had to patch it everywhere.
Yeah. It really highlights how deeply you need to understand the subdependency graphs of the tools you're using.
That makes sense for Conda users. But what about standard native Windows machines? Not everyone uses Conda.
Right. And native Windows doesn't have a unified centralized system package manager in the same way Linux has apt or macOS has Homebrew. Standard Windows just doesn't install C++ libraries into a global system path by default.
Weens, the find package command, looks around the standard Windows directories, finds absolutely nothing, stays perfectly quiet, and the CPM fallback activates seamlessly.
Exactly. The graceful degradation works perfectly. Standard Windows users experience 0 regression in build times. It stays at 15 minutes, just waiting patiently for the day. Windows adopts a native package manager that CMake can actually easily interface with.
That is so clean. So having perfected the pattern and solved the linker conflicts, it was time to scale. We're finally moving from theory, from a neat idea on one developer's laptop, to a massive automated execution across an entire organization's code base.
And the scale of this rollout is what really elevates this from a neat trick to a major structural engineering feat. The presentation outlines that they applied this pattern to 24 C++ header-only repositories within the Lux036 organization.
Wow.
Yeah, targeting dependencies like FMT, cdlog, doctest, and of course, AppSale.
For context, for those listening, a header-only repository means the library doesn't have a separate compilation step to build a .del or a static library file.
Right, no pre-compiled binaries.
Exactly. All the implementation code is written directly in the .h or .hpp header files. The compiler just pastes that code directly into your project wherever you include it.
Which makes distributing the library incredibly easy.
Super easy. But it means the burden of parsing and compiling all that code falls entirely on the end user every single time they build. If you have 24 repositories structured this way, the compilation overhead across an entire engineering team is just staggering.
And to roll out the fix, they didn't just manually open 24 repositories. paste code into 24 CMakeLists.txt files and manually open 24 pull requests.
Thank goodness.
The presentation notes this was executed in one orchestrated session using what they call parallel subagents.
I am still reeling from that detail. We'll dive into the implications of AI agents doing organizational refactoring in a second, but the return on investment here is incredible. Across those 24 repositories, these subagents modified roughly 56 files.
Right. They only added about 6 lines of code per dependency.
So like 200 lines of code changed total
Yeah.
across the entire ecosystem.
Yeah, a tiny footprint.
And the result, for 80% of the developers, the ones working on Linux and macOS with package managers installed, their build times dropped from 15 minutes to 30 seconds.
A 30x speed up in compilation time. Just massive.
Think about the reclaimed flow state there. Instead of hitting compile, getting up, grabbing a coffee, checking your messages, and completely losing your train of thought for 15 minutes, you're waiting 30 seconds.
You barely have time to stretch your legs before the build is done.
That kind of iteration speed completely changes how aggressive developers can be with testing and refactoring.
Absolutely. But what is equally critical to the success of a rollout this large is the impact on CI, the continuous integration pipeline.
Wait, I wanted to ask about this. If CI pipelines are designed to test fresh, clean builds every time a developer pushes code, wouldn't changing how dependencies are fetched completely destroy the pipeline?
You would honestly think so. CI servers are notoriously brittle.
So brittle.
But the presentation explicitly states the CI impact was practically zero. Because if you think about the nature of a CI runner, it is essentially a sterile, blank slate environment.
Of course. A CI runner running on GitHub Actions or GitLab doesn't have a developer casually running brew install absil in the background on a Tuesday.
Exactly.
It doesn't have system packages pre-installed unless you specifically write a step to install them.
Right. So when the CI server runs the newly modified CMakeLists.txt file, the find package command searches that sterile environment, finds nothing, and quietly fails. The CPM fallback activates, and it behaves identically to how it behaved before the optimization.
But wait, doesn't that mean the CI server is still taking 15 minutes to build?
No, because CI servers utilize really aggressive caching mechanisms like the GitHub Actions cache to store the CPM source directories between runs.
Oh.
Yeah, so once it falls back to CPM, it hits the cache, bypasses the download, and stays fast.
That is brilliant. The two-step fallback perfectly threads the needle. It optimizes the local developer experience without requiring a massive overhaul of the remote CI infrastructure.
The source does note there was one minor cost, though. A one-time cache miss on the very first CI run right after the update.
Just because the files changed.
Yeah. Because the subagents modified the CMakeList.txt files, the hash of the file changed, which invalidates the previous cache key. But honestly, a one-time 15-minute penalty for a permanent organizational upgrade is a trade literally any engineering manager will gladly make.
Oh, in a heartbeat. So what does this all mean? We've gone through the agonizing problem of the clean build, the elegant cross-platform manual fallback, the complex Windows linker conflicts, and this wild automated rollout.
The presentation distills everything down to what Luck 036 calls the golden rule, which is this. The best optimization is the one you don't have to run.
I love that. The best optimization is the one you don't have to run.
Never force your users or your own local machine to compile code from source if a system package manager can help. Is a fundamental shift in perspective.
Instead of obsessing over how to make the compiler run faster or how to write clever C++ to speed up parsing, you ask, how do we avoid compiling this altogether?
Exactly. You offload the work to the ecosystem.
It's profound. And based on the source's roadmap, Look 036 isn't stopping here either. The presentation outlines plans to apply this pattern to remaining heavy dependencies like GSL, NanoBench, and CPB.coro.
They are also looking at integrating CMake presets.
Ooh, what do those do?
Presets basically allow you to define platform-specific configurations in a JSON file. This would make finding system install locations even more robust, especially on complex enterprise setups.
Nice.
They also plan to expand support beyond just OS package managers to include dedicated C++ package managers like VCPKG and Conan.
Meaning, this pattern will soon cover almost every conceivable way a developer might have a library installed on their machine.
Yeah, it's basically a comprehensive blueprint for the future of C++ project configuration.
It really is. Before we wrap up, though, I want to leave you, the listener, with a final thought to mull over. something that builds on this presentation but points to a rapidly approaching, slightly wild future. Oh, I mentioned it briefly during the rollout phase. The source casually drops the fact that parallel subagents orchestrated this entire code modification across 24 repositories in a single session.
Yeah, the phrasing is just sitting there on the slide, almost as an afterthought, like it's no big deal.
Right, but think about the mechanics of what those agents actually had to do. They weren't just running a blind find-and-replace script.
Definitely not.
An AI agent had to clone a repository, parse the cmakelist.txt file, understand the dependency graph well enough to safely inject the find package quiet logic without breaking existing targets.
And ensure flags like SPD allo gf mtexternal were added where necessary.
Yes, then commit the changes and open a pull request. And it did this concurrently across 24 code bases.
The ability for an automated system to comprehend structural build logic and safely refactor it across an entire organization totally changes the definition of software maintenance.
It really does. How long until these agents aren't just executing a plan a human came up with, but proactively finding the bottlenecks themselves?
That's the logical next step.
Are we moving toward a world where you go to sleep and overnight an agent realizes your project's build time has crept up to 5 minutes, analyzes the dependency tree, tests a new caching strategy, and just has a pull request waiting for you in the morning that cuts it back down to 30 seconds?
It's totally plausible. The friction of development is being smoothed away, not just by better code, but by intelligent automation handling the plumbing we used to fight manually.
If AI can orchestrate the fix for a 15-minute compile bottleneck today, how long until the code base simply optimizes itself? It's a thrilling thought to explore on your own.
It really is.
Well, thank you for joining us on this deep dive. We hope it encourages you to keep questioning the bottlenecks in your own daily workflows. Look for those places where you are building the engines from scratch and ask yourself, is there a way I can just grab the keys,